Okay. Last time we proved Kepler's three laws. We did finish the third law, now let us calculate the energy. First, we had the semi-major axis. Last time we had this, and the algebra you can go through. The final result is the interesting thing here is that this energy, this means that the energy in the book, this formula was given, but it was not derived because there were no discussion of how the orbit is an ellipse. It's very interesting that this energy only depends on A. On the semi-major axis. That means it's independent. It is independent of the eccentricity. So that means that a circular orbit and an elliptical orbit like this, if they have the same major axis, if the length of this ellipse is the same as the diameter of the circle, then they have exactly the same energy. This ellipse I drew did not look like an ellipse. Look into the book. In the book there is this diagram, and it shows several ellipses of the same A, but with different eccentricity. And the interesting thing is that they all have the same energy. So we have finished talking about the case of an elliptical orbit. Now we talk about the second case where the energy is equal to zero. The first one that we talked about is energy less than zero, and that gave an ellipse. Now we talk about the energy equal to zero. We go back to the equation. The equation becomes this. Originally there were two terms on the right hand side, but the A term is now zero. So we have this, where B is equal to 2 mg over c squared. In this case, we again put r equal to 1 over rho, and then we get d rho d theta squared is equal to b rho minus rho squared. For the case E not equal to zero, there's one more term. So we're perfect square. And again we put sigma equal to rho minus b over 2. Then the equation becomes d sigma d theta So this is very similar to what we have, and we put sigma. Whenever you see an equation like this, you know you should put the sigma equal to b over 2 times sine phi. If you substitute that, you get d sigma d phi times b over 2 cosine phi. So you get d sigma d phi squared is equal to 1. This is very similar to what we had. So we take d sigma d phi equal to plus 1. You can take it equal to minus 1 where the result is the same. So we get sigma, no, not d sigma, d theta d phi. Just a minute. So sigma is equal to phi plus a constant. So rho is equal to b over 2 plus sigma. Something's wrong. Just a minute. This is wrong. This is d phi, d theta. So d phi d theta square is equal to 1. So phi is equal to theta plus a constant. The minus 1 we forget about. So we get rho 1 over r is equal to rho, which is equal to b over 2 plus sigma. Plus sigma becomes b over 2 sine of phi. Sine of phi is sine of theta plus constant. But that constant, if you rotate the coordinates, you can forget about the constant. So we now have the formula 1 over r is equal to b over 2 times 1 plus sine of phi. This is equivalent to the previous case, i.e. E is equal to 1. How do we change this into Cartesian coordinates? Cartesian coordinate 就是正交的这个 x 跟 y， 这就是同样的，我们把这个变成1 equal to b over 2 times r plus e y. So we get r is equal to 2 over b minus ey. So I square this, I get x squared plus y squared is equal to 4 over b squared minus 4ey over b plus e squared y squared. Therefore, we get x squared plus e is equal to 1. So y squared is cancelled. So x squared becomes equal to 4 over b squared minus 4ey over b. That's a parabola. When x is equal to 0, y is equal to the ratio of 2, so it's here. When y is equal to 0, x is, so you get a curve like this. So Newton proved that if the energy is equal to 0, the orbit would be like this. In fact, there are comets which does exactly this. When E is equal to 0, you put that into the kinetic energy plus the potential energy is equal to 0 in this case. The potential energy is equal to 0 at infinity. So at infinity, the potential energy is 0, the total energy is 0, so the kinetic energy is 0. That means that its velocity is 0. So it's a particle which starts with a very small velocity, no velocity, and it gets attracted to the sun. If it heads straight for the sun, it will hit the sun. But usually it's not exactly straight, so then it goes faster and faster, and then it swings around and then goes out again. And that indeed is the trajectory of many comets. Now the third case is E greater than 0. In this case, at infinity, the particle comes with a finite velocity. So we do exactly the same thing. You get d theta squared plus r squared is equal to, in this case, this term is positive. Again, we put 1 over r is equal to rho, and we get 1 over rho fourth times d rho d theta squared plus 1 over rho squared is equal to d squared 1 over rho fourth plus b rho third. So d rho d theta squared is equal to d squared plus b rho minus rho squared. Again, we perfect squares. This becomes rho minus b over 2 squared plus b squared over 4 minus plus d squared. So again, we put rho minus b over 2 as sigma. Etc. This is all the same, and we eventually get 1 over r equal to rho equal to b over 2 1 plus e sine phi. Exactly the same equation, but in this case alpha is equal to square root of 1 plus 2c squared over m squared g squared e over m. And it's greater than 1. So we get the same formula for the three cases, but E for the ellipse is less than 1, for parabola is equal to 1, for now it's greater than 1, and this is a hyperbola. If we do the same thing, we multiply it out and then do what we did before, we eventually find the following equation: e squared minus 1 y squared minus x squared is equal to alpha squared e squared minus 1. Alpha is equal to 2 over b. So what does look like? What does this look like? Let this be y prime. We take y prime. Sorry, this is y prime. And y prime is equal to y minus e alpha divided by alpha x squared minus 1. The original coordinate is here. This is the sun. Y prime, the sun is at the x equal to 0, y equal to 0. The sun is at r equal to 0. That means x equal to 0, y equal to 0. But we have shifted the coordinate by this. And the curves look like this. The particle comes here. This branch is not touched by the planet. The planet comes here and goes out here. It's very much like the parabola, only it is a hyperbola. A hyperbola is more straight than a parabola would be like this. A parabola is bent a little bit more. This is a hyperbola. So Newton in the Principia in 1687, in a few chapters, had completely solved the planetary motion, and he called that the system of the world. Why the system of the world? Because at that time, of course, the most important thing is the planetary system. He lived on for another 30 years. He was not a pleasant man. He never married, and he became the chief of the mint. The mint 是造币厂. He became the British head of 造币厂, and he was a very powerful person. But his discovery was universally recognized as a great event. Sometimes there is the mistaken notion that the Industrial Revolution started with Newton. That is not true. His work did not immediately produce any industrial fallout, did not create any new productivity. That came later. But intellectually, it was recognized within a few years that here was a great discovery. Why was it a great discovery? Because for the first time, mankind understood that nature has precise laws, and that these laws are in mathematical terms, and that we can understand these precise laws. So you might say that that is the beginning of modern science. Science existed already before Newton, existed both in China and in Europe, but it was empirical, 是经验性的. It was not founded on precise mathematical terms. The fact that people understood that there are precise natural laws, that started with Newton. So at the time that Newton died, it was he was very well known, and he was eulogized by many people. In particular, here's a poem. One of the great poets of that time was Alexander Pope, who was born in 1688, and he wrote two lines. Nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light. 我把这个翻译成自然与自然规律为黑暗隐蔽，上帝说让牛顿来，一切遂真光明。这是历史上非常有名的两句话。我们来看一下爱因斯坦在这个世纪怎么讲的关于 Newton。Einstein in 1971 once said, "Fortunate Newton, happy childhood of science. In one person, he combined the experimenter, the theorist, the mechanic, and not least the artist in exposition. He stands before us strong, certain, and alone." I think there is no dispute that Newton's work started modern science. But there were people who were a little bit jealous, 有点妒忌他。One of them was Lagrange. Lagrange was about 100 years later than Newton, so he never saw Newton. But he was a great mathematician. He and Laplace developed Newton's mechanics. I have more to say about that later. But anyway, he was a great mathematician. And he greatly admired what Newton had done. But he said the following. He said, "Newton was assuredly the man of genius par excellence. but we must agree that he was also the luckiest. One finds only once the system of the world to be established. 所以他是有点嫉妒，说是大家本来不晓得，不 understand the system of the world， 等着 Newton 去发现。他这句话当然就包含说是，要是 Newton 没发现，我就来了。他又说 ，How lucky Newton was that in his time the system of the world still remained to be discovered. I said this also for the following reason. The success of a scientist very much depends on his times. It's if you move Newton to another time after the system of the world has already been discovered by somebody else, then it is clear that the Newton's contribution would not have been as great as it had been. So Lagrange was correct. And again, if Einstein were not born at the time that he was born, at a time when special relativity, general relativity were not discovered, it is difficult to, for example, if he were born 40 years later, it is difficult to imagine that he would have made as great contributions. How does that affect you? That means that your future is intimately tied with the present scientific and technological progress. There is no way in which one can escape that. So you must, in some sense, realize what the present scientific and technological developments are like in general, and find for yourself the direction in it in which you could make the maximum contribution. Newton's Principia did not contain only what I just told you about the ellipse, the parabola, the hyperbola. What we described is called the two-body problem. How about other things? The Principia contains many other things. For example, it contains the discussions of the tide. This is a highly complex phenomenon because the ocean is influenced by the attraction of the sun on the earth and of the moon on earth. So the tide is deeply related to the relative position of the sun, the moon, and the earth. And Newton had a complicated discussion of this fact. Newton had discussed three-body problem. The most important three-body problem is, of course, the motion of the moon relative to the sun and the earth. Now, in contrast to the two-body problem, which Newton solved for all cases, the three-body problem cannot be solved. There is no simple solution of the three-body problem. No simple solution at that time, no simple solution today. And that is still a problem which many mathematicians work on. In particular, there is the question of the existence of singularities. In the two-body problem, if a particle heads to the sun, But head on, I had mentioned this earlier, it would crash into the sun. That would be a singularity. But that is a very rare event. The question of whether there are singularities with many bodies is still a very complicated subject which is being investigated. And one of the problems of the singularity for a many particle system is called the Penn-LaVey conjecture. Penn-LaVey was an important mathematician 100 years ago. And 100 years ago, he made a conjecture about the many-body problem. And people have worked on it for about 100 years. It was solved about 10 years ago by Xia Zhihong. I'm not sure 他这个名字是这样写法的。这个我知道因是夏志宏，我没见过这位。我想他现在大概是45 years old. He graduated from Nanjing 大学 and in the astronomy department. Then he went to the United States. He became famous about 10 years ago because he solved the Penn-LaVey conjecture. Or rather, he produced an example which had great relevance to Penn-LaVey's conjecture. In that area, there are still people who are working on it. The field that he is in is called dynamics. It's also called 混沌理论。混沌的沌字怎么写法？3点水一个，不是顿。我不会写这字。他这个 Penn-LaVey 的 conjecture 是 for many body problem。那么要证明出一个 singularity， 第一个人证明出来有那么一个 singular 的 many body problem 是夏志宏做的，他是 five body， 他制造出来一个 five body 的 motion， 这个 motion 它可以证明是是有 singularity， 混沌这样写法，混沌理论，这是现在很热门的一个题目。Okay, for the gravitational force 1/r², we have discussed in detail. we have discussed in detail the case of the 1 over r squared. How about the, let's say, 1 over r cubed force? In that case, the potential energy is not 1 over r, but 1 over r squared. Because if you take the derivative of this, the force is minus du dr, and that's equal to minus 2g over r cubed. In that case, we can go through the whole the same argument. We have the energy is equal to m over 2 c squared over r. We still have r squared theta dot equal to c. This is because angular momentum conservation is still valid. So we get this. So we get dr d theta plus r squared is equal to a r fourth plus b r squared.现在我们要分成好几项，第一项是1小于0。So the particle would not escape. In this case, that means A是小于0，因为 A 是 proportional to E 的。The left side is positive. This is negative. So B has to be greater than 0. So this equation可以写成这样。我写 A bar 等于 minus A， 所以 A bar 是个 positive quantity。那么同样，我们把 r 等于 1 over rho， 那你把这个变一下呢，就等于说 d rho d theta squared 就变成 b rho squared 减去 A bar。这个跟从前不一样的地方是这个 rho squared 这是 rho squared 的 sign 跟从前不一样。要处理这个的话，我们现在 put square root of b theta 叫做 theta prime。为什么呢？ Because if you divide this, you want the rho squared to have a coefficient 1, so you divide by b. If you divide by b, the denominator, and you take square root of b times theta, you call that theta prime. Then it becomes simpler because it becomes d rho d theta prime squared is equal to rho squared minus A bar over B.我们把这个叫做 rho squared minus Q squared. Q 是等于 square root of all those are very similar to what we had before, except for a sign change. It's no longer minus rho squared. It now becomes plus rho squared. Does anybody know what we should do next? If it were the other way, if it's Q squared minus rho squared, what did we do? we put rho equal to q times sine phi. Now we have changed sign. Does anybody know what we should do? If anybody knows, raise your hand. 李真，你晓得不晓得应该做什么？OK, thank you. 凡是遇到这种情形，你就把 sine 变成 hyperbolic sine. 所以 put rho equal to q times hyperbolic sine 或者 hyperbolic cosine. 应该 take hyperbolic cosine. Hyperbolic cosine 跟 hyperbolic sine 它的 definition cos of phi 是等于1/2 phi plus 1 minus phi. Sinh 就是 hyperbolic sine 是等于1/2 phi minus 1 to the minus phi. Hyperbolic cosine, hyperbolic sine 跟 sine 跟这个普通的 sine 跟 cosine 是 deeply related， 就是差了一个 i。这个你们假如不familiar, it's good to become familiar. If you want to become a experimental physicist, you don't need to be very familiar with hyperbolic sine and hyperbolic cosine. But if you want to become a theorist, you better learn hyperbolic sine, hyperbolic cosine. For example, there is a formula which says hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. This is very similar to the sine and cosine, except it's a minus 1 instead of plus 1. I mean, the hyperbolic sign in front of it is a minus sign instead of a plus sign. After you have put that in, the differential equation becomes q, the derivative of cos is equal to sinh. But that is equal to sinh squared. The trick is extremely similar to the sine case. So you eliminate those, you get d phi d theta is equal to 1. And so therefore you get 1 over r is equal to rho q. This gives d phi d theta is equal to 1. So this is equal to this is theta. I'm assigning the next steps of this calculation as an exercise for next week. I want you to plot. It's a very interesting curve. The particle does not escape because E is less than 1. Next, we talk about E equal to 1. E equal to 0. In this case, the differential equation has the a bar term becomes 0. So therefore, you get 0 you get dr d theta squared plus r squared is equal to dr squared. So we get dr d theta squared is equal to b minus 1 r squared. So b has to be greater than 1. So we get dr d theta prime squared is equal to r squared, where theta prime is equal to square root of b minus 1 times theta. So dr d theta prime is equal to r. So theta prime d theta prime is equal to dr over r is equal to log of r plus a constant is equal to d log of r plus a constant. This is a natural logarithm. That means logarithm with respect to e. So theta prime minus the constant, let's call this C1. Theta prime minus C1 is equal to log of r, or r is equal to exponential theta prime minus C1. I will not plot this, you get the spiral. So in both of these cases, and also for the third one, the third case is E greater than 0. I'll not go through the details. You also get a spiral. So for this case, one would not get a closed orbit. You always get some very complicated rotation. It is in fact very, very fortunate that the fourth law is 1 over r squared. If it's not 1 over r squared, it's 1 over r to the power 2 plus delta, then the orbit would not be closed. If it is not closed, it would be very confusing to the early astronomer, and there would never have been any easy discovery ready for Newton to do. And there probably would be very difficult to have modern science. So how come? Why is it that nature did things such that it is possible for mankind to discover precise natural laws? Well, we do not have the answer to that question.
However, we know now that there are other reasons for it being 1 over r squared. In other words, one almost could have said that the reason that it is 1 over r squared is because God knew that with 1 over r squared the orbits would be simple, and therefore mankind could discover natural laws. Some people would immediately believe that idea. But we now know there are other things peculiar to the 1 over r squared. Because as you will learn later, when you learn electromagnetism, in electromagnetism there's also 1 over r squared. And that was discovered in the 19th century. In the 20th century, we now know even more, that both the 1 over r squared of Newton's law and the 1 over r squared of the Coulomb's law in electromagnetism are both related to an even more general concept. And that the concept is one of the great achievements of 20th century physics. But and that's a very beautiful principle. But that still does not come to the end of the question, because there is still the question, why that beautiful structure? So once you get into such kind of thinking, you would realize that the science continues to make progress, and these progress are very beautiful. But science cannot answer all questions, because in the end there's the question of why your last understanding. So that's why I always say that in the end, if you want to raise too many questions, you would become religious.
Okay, now we go to the next chapter. We all know that there are solids, there are liquids, there are gases. The book calls these two fluid.流体。流体的 characteristic 没有 shear。假如你是一个缸，你把这个拿住了，你这样，你底下拴住了，上面呢，那它就产生叫做 shear。We have discussed that before. Liquid, there's no shear. It has no resistance. By the way, I want to introduce the concept of intensive and extensive quantities.我不知道 intensive 跟 extensive 中文翻成什么？
let me, and this is not in the book, but the reason I'm introducing it to you is because a student asked me,
在这个 Young's modulus 的时候，我们这书上面有一个 formula 我也写下来了，是 force divided by area， 这是一个棍子，我把它拉长了，这个拉长的 distance 叫 delta L。这棍子的长度是 L， 你把它拉长了，我们有这么一个 formula， 这个 formula 这 E
叫做 Young's modulus。有一个学生来跟我说，他说你为什么要底下用个 L？ 他说 all that I know is that if you stretch it by not very much, the force is proportional to delta L.
So he believes that he would easily agree to F over L is equal to some constant times delta L.
But why does the book write it as E over L? Answer.
这个 quantity delta L over L 是一个 intensive quantity， 而 delta L 是 extensive。
什么叫做 intensive？ 什么叫 extensive 呢？先讲 intensive。如果你这个你把这个拉长了，我现在 consider 它的一半，那么那一半的那个地方的 delta L is 1/2 of delta L, and the length is also 1/2. So delta L over L is the same whether you talk about this or you talk about 1/2 of it, or you talk about 1/4 of it. That's the meaning of intensive. Intensive 的意思就是它与那东西大小没有关系。假如你是只用 delta L 的话呢，那你看整个一个棍子是 delta L， 你看一半的棍子就一半 delta L， 所以 delta L 是一个 extensive quantity， 而这个 delta L over L 是一个 intensive quantity。那么像这种 formula， 你的目的就是要 write relations between intensive quantities， 所以与你的这个棍子多长没有关系。那么这个就变成 intensive， 因为 delta L over L 是 intensive，F over A 也是 intensive。你把这个的一个棍子拉长的话，你随便在什么地方切 ，the force divided by area is the same.
So this is the formula of intensive. Therefore, this E is intensive. If you had not had this L, then this is intensive. Delta L is extensive.
So this E has to be also extensive, and you don't want an extensive quantity. So this difference between intensive and extensive is a very important one.
我们现在要 talk about the fluid 的时候，我们要 talk about pressure。pressure 是等于 force per area。所以它的 unit 这个 unit 叫做 Pascal。简写成 PA。它的 unit 是1个 Newton， 在我们这 system 里头，当然是 per meter squared。那么一个 atmosphere turns out 是等于 1.01 乘上10的5次方 Pascal，
所以一个 Pascal 是个很小的 pressure。
这个书上有一个题目，是在这个 figure 15，这面是 T， 是 temperature in degree C， 这是2000度， 这是1000度、2000度、3000度，然后这个地方是 gigapascal， 一个 giga 就是10的9次方。这个叫做一个 phase diagram。这面是 graphite， 这面是 diamond。Graphite， 我不知道whether you have seen graphite. Graphite is a kind of if you have a graphite sheet, it's 你用手一摸就是要弄得你手都是黑的，是叫做石墨。那么 graphite 跟diamond 都是 carbon， 就是它的 chemical 的 composition 是 carbon。不过呢，它是不同的 crystal structure。graphite 是一个 crystal structure，diamond 是一个 crystal structure。假如你在1000度的时候，这面是 pressure。假如你在1000度的时候，你把这个 graphite 拿来，它这个地方是0，这 pressure 是0，这是2个 gigapascal， 这是4个 gigapascal。一个 gigapascal 那是很大了，那是有几万个，差不多有1万个atmosphere。所以你用很大的压力把它压的话呢，它一直都是 graphite。可是到了这一点的时候，到了够多的 pressure 的时候，它要变成了 diamond。diamond 当然大家晓得跟 graphite 是完全不一样的 ，graphite 是黑的 ，diamond 是白的。graphite 是不透明的 ，diamond 是透明的，所以这就是有不同的 crystal structure。我要你们注意啊 ，both T and P are intensive quantities。换句话说，你拿了一块石墨，它里头每一个地方的 T 都是一样的，每一个地方的 P 也都是一样的，所以 P and T are intensive quantities。平常的一个简单的 substance， 你要知道它的 state， 你要告诉他你要讲出2件事情来。One is the pressure it is under, the second is its temperature. For more complicated things, you may need to specify more things. We'll come to that later. 这是从书上找出来的另外一个 phase diagram， 这是 P， 这是 T。那么在这个情形之下 ，the pressure is not so high，and 这个是水的phase diagram。这是essentially是0度，然后这是100度，这是这100度 C。那么在这一块的是水，我们let's understand what's going on。这是一个 atmosphere， 这就是平常的 atmosphere。那么在这上面，它的意思是这样：假如你比如说你在这儿，你超过了 you have a heated system， then it becomes a vapor. So at this point you have a vapor. Now you cool it. At this point, at 100 degrees, it condenses into water. If you further cool it, it will go into the phase of water. So this is called a phase diagram. 我们大家都知道 as you cool water at 1 atmosphere, when you reach 0 degrees, it would begin to freeze. And if you further cool it down, it becomes ice. So this is the phase diagram. Now, if you go to a lower atmosphere, for example, if you go to higher altitude, the atmospheric pressure becomes less. In that case, water begins to boil at a lower temperature, and it begins to freeze at a higher temperature until you reach this point. It's 4.5 millimeter mercury. One atmosphere is 760 millimeter mercury. So this is a very low pressure. When it gets to a very low pressure, this is called a triple point, where gas, water, and solid all become one phase. If you go lower, then the gas would become solid without going through the liquid phase. So this is a typical case. This is a gas phase, this is a liquid phase, this is a solid phase. But if the pressure is very low, you can go from the gas to the solid phase without going through the liquid. This is a kind of a typical phase diagram. But actually it's very complicated, because if you go to very high pressures, then water would become ice. But it turns out that there's many kinds of ice. So if you go higher, this is a very complicated diagram. It has more branches, because ice is a crystal. If you compress it too much, it would change the crystal structure. So then you would have other phase transitions. These lines are called phase transitions. And higher up, you have very complicated phase transitions. The study of phases of material is a very important subject. The theory of phase transitions is another important subject. And we'll touch on this a little bit later. So now we talk about the phases. Your gas, your liquid, your solid. But this line terminated at this point. What that means is, if you are at this point, you have at this pressure, gas, liquid, and solid transition is like what we usually know at 1 atmosphere. But if you go above this point, there is no transition. What that means is that you can go from gas to liquid without a phase transition. This is a very strange phenomenon, because originally in the early 19th century, people thought that these phases are very different. So gas is different from liquid, not only because one is denser than the other one. Gas is, of course, less dense than the liquid. Not only because of that, but also because if you want to change from a gas to a liquid, you have to go through a phase transition like this. But then in the late 19th century, people have found that in fact you can have this case where you can go from the gas without crossing any phase line, transition line, into another phase. So in fact, gas and liquid, the division is not absolute. And that was a great discovery. So these kind of points where the phase transition line stops is
another very interesting subject. This triple point is another very interesting subject. And one of the important discoveries of 20th century physics was to have a detailed understanding of why there are phase transitions, why there could be this termination of phase transitions, and so on and so forth. In 1913, there was another discovery, namely that you can have superfluids. There was a phase transition. It's a new kind of phase transition, which is a phase transition which goes between superfluid and normal fluid. This was a discovery by Caroline Onnes. He got the Nobel Prize. He was a great experimental physicist in a small country, the Netherlands, Holland. He alone was able to go to very low temperatures, to let's say around to below 2 degrees absolute. The meaning of absolute temperature will come back to later, but 0 degree absolute is minus 273, about minus 273 degrees centigrade. And he alone in the whole world was able to reach such low temperatures, and he dominated that kind of experiment for at least 10 years. It was only 10 years later that Oxford began to be able to produce such low temperatures. And since he was able to produce this low temperature, he just started to test the properties of various things under such low temperatures. And he found that many metals lose their resistivity. Before that, people already knew that there is, if you have a wire, it has how many ohms of resistance, and you can measure that resistivity. And resistivity is something very important, because if you want to transport electric energy from one source to another source, that transportation would require some energy. So all these power lines loses energy. So it was well known by that time that all metals have resistance. But around 1913, he found lead at very low temperatures loses resistivity. He was in fact amazed. He made a coil, and he produced a current in it, and just let it sit for a while. Now, at ordinary temperatures, it would quickly die down because it wastes energy. So eventually, all the energy becomes heat, and there's no more electricity. So the electricity would exponentially go down. But he found that at very low temperatures it doesn't go down. In fact, he produced a coil with current, and after several months he went back and found that the current was still there, and he was very amazed. That was called the superconductivity. So that is a new phase. And later on there were other superconductors found, and then there were superfluids found. So these are super liquids found. So in some sense, that's another kind of phase transition. There's last month, 2 months ago,
a publication September 2004. There's a discovery by Moses Chen.
Moses Chen was born in Shanghai, and he got his high school education in Shanghai. Then he went to America, and he's now a professor at Pennsylvania State University.
And he found super solid. It's another transition.
This is a profound discovery. I would think he might win a Nobel Prize for this, because before that there was superfluid, helium-4 and helium-3 at low temperatures both become superfluids, but there was no solid which can become which has a super property.
And he found the super property.
We have invited him to come to give some lectures. So next year in June, he will give a series of lectures about his new discovery. Actually, the experiment is extremely simple. It's just a small bucket， 一个小桶子，里头放了helium-4， 然后把这个 helium-4 at low temperature and high pressure, it becomes a solid. That was known before. But what he did was he took this solid and rotated it. Now if you rotate it, you can measure its moment of inertia. We have learned about the moment of inertia. And he found that when the temperature is low enough, the moment of inertia suddenly changes. It suddenly becomes if the original at high temperature, there's a moment of inertia I. When you lower the temperature, the moment of inertia suddenly becomes 99% times I. In other words, it loses some moment of inertia. And the explanation is that when the solid rotates, a part of it doesn't rotate. So the solid becomes a super part and a normal part. The normal part is a solid which rotates. The super part remains not moving. As a consequence, it does not contribute to the moment of inertia. So his moment of inertia becomes less by only 1% approximately. How can something move inside of a solid? That's the thing which makes this discovery unexpected. It's one of the very exciting new discoveries in physics. So traditionally we have gas, liquid, solid. The solid can have different phases because it can have different crystal structure. Now we know that the liquid can also have super phase and non-super phase. And now we know the solid can have super phase and non-super phase. All of these go under the idea of long-range order. What is meant by long-range order? A crystal has long-range order. A liquid and a gas does not have long-range order. Why do I say this? Because if you take a crystal, let's say sodium chloride, it's a yen, then if you know one atom of the sodium chloride, then at a very large distance you know that it's not absolutely arbitrary. For example, if you not only know the one atom of sodium chloride, and if you rotate it, after it's lined up, you know that at a large distance, the distribution of the crystal of the other atoms follows a periodic system. At infinite distance, there is still an order. So that's called long-range order. A superfluid also has long-range order, and I'm very proud that I invented a term. It's called off-diagonal long-range order. That terminology means that the ordinary long-range order is a diagonal long-range order. So a crystal has diagonal long-range order, but the super phenomena means that there is an off-diagonal long-range order. Now, what is the meaning of diagonal or off-diagonal? And this is a difference between classical physics and the quantum physics. With a quantum phenomena, there are diagonal and non-diagonal things. I had repeatedly mentioned to you that Heisenberg, without understanding what he was doing mathematically, stumbled on quantum mechanics, and he used a matrix. Quantum mechanics is based on matrices. Matrices have diagonal elements and off-diagonal elements. So in classical physics, there's no difference between diagonal and off-diagonal ideas. But in quantum physics, there's a difference between diagonal and off-diagonal. And the ordinary long-range order of a crystal is a diagonal long-range order. All these super phenomena are related to long-range order in the off-diagonal. This is a subject which is not yet completely understood, and that is why it is people are especially interested in the new discovery of Moses Chen. Okay, I finished what I prepared to tell you today. So this coming Sunday at 3 o'clock in this room, I'm going to give a talk. It's only for the students in this class. I hope some of you would find my talk very interesting.